In this video, we're going to be talking about transformations of two random variables. So let's say we want to find a joint PDF of w and z, and we're given w and z as functions of x and y. So let's say we can find the inverse of this transformation. What I mean is saying that we can write x as a function of w and z, and y as a function of w and z. Then we can find the joint PDF of w and z by plugging in the function for x in terms of w and z, same for y, and then multiplying by this what looks like absolute value of j term. So first, before we write down what this j is, I want to notice that this looks a lot like our formula that we just had in the previous section, right? This looks like f evaluated at the function of the variable times the absolute value of, well, in that case it was the derivative, and we're going to see that this is related to the derivative here in just a second. Okay. So this has the same type of form. So let's talk about what this j is. Well, if you've seen Calc 3, j is the Jacobian. It's basically, it's a transformation of two variables to two variables, or say three variables to three variables. It has to be square, but when we do the Jacobian, we do the determinant. That's what these absolute value bar looking things means. Do the determinant of, we take the partial with respect to w for r, partial with respect to z for r, w for s, and then w for, or z for s as well. When you do the determinant, you take your product of your terms on the diagonal here and subtract the product of the terms on the off diagonal here. So we would take this determinant and then do the absolute value. Okay. So that's how we do the Jacobian. So let's see how we do that here in a second. We've got, in this example, x and y have a joint PDF that's constant, so it's uniform over this rectangle. And we want to find the joint PDF of w and z, where w is x plus 2y and z is 2x plus y. Alright, so the first thing we have to do is invert this transformation, meaning we need to get x and y in terms of w and z. So the first thing we'll do is we'll solve the second one for y. We'll plug that into the expression for w. And so we get w here in terms of x and z, but we want x in terms of w and z. So gather like terms here, we get a negative 3x and a positive 2z. Well, swap them things around, divide by 3. You get x is equal to 1/3 times negative w plus 2z. Plugging that in now in for the expression that we have for y, we get y is 1/3 times 2w minus z. So if you've done a solving system of equations, it's exactly what we're doing. We're just writing one variable in terms of another, plugging it in and solving. Just in this case, our variables, we have variables rather than numbers than we're used to doing. Okay, so now we find the Jacobian. The Jacobian says you take the partial of r with respect to w, partial of r with respect to z, and do the same thing for s. So our r function, remember, is our x. So we would take the derivative with respect to w, we get negative 1/3. Derivative with respect to z, we get positive 2/3. And the s function refers to the y. Partial with respect to w here is 2/3. With respect to z, it's negative 1/3. So we get this determinant we need to compute. 1/9 minus 4/9 gives us negative 1/3. Okay. So now the formula says that we take the functions that we just found, plug them in for x and y, and multiply by the absolute value of the Jacobian. Well, the absolute value of the Jacobian is just 1/3. We had a constant PDF, which is 1/6, so we just get 1/18. Alright, so let's see what the support now is for w and z. When we do this, we just look at what happens to the boundaries. So remember, it was x went from 0 to 2, y went from 0 to 3. So if we look at the boundary x equal to 0, so that would be the left bound, if you will, on the rectangle. Well, if we set that x equal to 0, then we get w is equal to 2z. So we get this linear relationship between what w and z must be. And then the same thing for if x is equal to 2. That would be the right side of the rectangle. Now let's do the bottom and top of the rectangle. If y is 0, we would set the y function equal to 0. We get w is 1/2 z. And then if y is 3, we get w is 1/2 z plus 9/2. So this gives you the boundary of the region that the xy region maps into. So if we look at a picture, here was the support for x and y. Remember, this line went to w equals 2z. This line went to w equals 2z minus 6. And then the other two lines as well. So here's your w equals 2z. This was the one that corresponded to x equals 0. This is the one that corresponded to x equals 2. Oops. This was the one that corresponded to y equals 0. And this one was the one that corresponded to y equals 3. So notice we get this rectangle ends up getting transformed into a parallelogram. We'll talk more about how we do some examples of these in class, but I wanted to give you an example of where we were going so that we can concentrate on just doing the examples in class.